Well, hello and welcome to the EMA Expo presentation today by Dr. Joseph Minow, who's going to provide to us an introduction to space environmental effects. My name is John Twarduk. I'll be your host for the presentation today. If you'd like to submit questions during the session, please use the Teams Q&A capability, which you'll find in the top center of the menu bar. And after the presentation, we'll address any submitted questions. If there are any questions that remain unanswered, we will address those via email. Our speaker today is Dr. Joseph Minow, who is a technical fellow at NASA. Joe began his career at Jacobs Engineering in 1998 at NASA Marshall Space Center, and there he worked to solve space environmental problems for projects such as the James Webb Telescope and the International Space Station, and later worked on the Space Shuttle and the Orion programs. His career has been primarily focused on characterizing space environments for space system design and operations, analysis and modeling of space plasma and ionizing radiation environments and their effects on space systems, investigation of spacecraft surface and bulk charging phenomenon, and investigation of on-orbit anomalies. He's contributed over 140 conference presentations, journal publications, and technical reports on the effects of space environments. Joe holds a bachelor's degree in chemistry and biology and a master's and PhD in physics, and we're very proud to have him address our audience today at the EMA Expo. So without further ado, I give the floor to you, Joe.
All right, thanks, John. So I was asked to talk about just examples of space environmental effects, and since most of my work over my career has been involved with spacecraft charging, I decided to focus on that today. And so I've got about 45 minutes worth of slides here, and I think, as John said, you can put questions in the Q&A. I guess if there's something in particular that's really, really important that you want to just break in and ask a question, I guess you can do that. But we can kind of take that as we go here. So let me go ahead and get my cursor over here. So spacecraft charging, has a variety of impacts on space systems, primarily in terms of electrostatic discharges, phantom commands, and things like that. It's interesting, over the years, there's been a number of studies, and the statistics that I have up here on the screen right now is over here on the left is from a study that was done at Aerospace Corporation about 25 years ago, looking at anomalies and failures on spacecraft that were attributed to the space environment. And of those, they determined that about half of them were due to electrostatic discharges, whether internal or surface charging, or some sort of a charging phenomenon that was uncharacterized. Which kind of makes charging a particularly important phenomenon in the space environment. And it's followed up by radiation effects, kind of another 35% or so on that. So charged particle environments in space are an important consideration for spacecraft design and operations. And say typically the issue that we have is when you charge up a spacecraft, when the potential gets too big and you have this excess charge density, you'll get a arcing on the system. And so this is an example down here on the bottom, kind of some ground-based tests that were done in support of an anomaly investigation for the Japanese ADIO satellite failure. And they were looking at material cracks and insulation on a power cable and arcing that was around that cable. And you can see this arcing damage can do quite a bit of damage to the power cable. So this, the risk to the spacecraft, when you get an arc, you can get RF noise from the arc, and that can produce phantom commands in electronic systems. You can get discharge currents to damage materials and damage electronic components. You can damage thermal control coatings and solar cells, as well as lead to trigger arcs on solar array power systems that can lead to sustained arcing and damage, and ultimately a failure of a power system. So it can be quite severe. And this is the figure here in the middle is kind of just an example of some arc pits, again, from a ground-based test. And this image on the bottom, again, is from this Japanese failure investigation from the ADIO satellite, showing these cables kind of before and after an arc, in the test chamber, and the kind of damage that you will get, the charring and the total destruction of the insulation in some cases. So over the years, there's been a lot of satellites, that have had anomalies and failures attributed to charging. And so this is a list that I kind of keep from a variety of sources. Some of these come from NOAA, anomaly reports. Some of them are from NASA. Some of them are, things that show up in the news periodically. And if you go through here, I guess I probably should have put a kind of a timeline together on some of this, but in the early years, from the 1970s kind of through the 90s, there was quite a lot of them. And if you kind of look down here, you'll see the kind of in recent years, it's probably not as bad. And I think that's because, charging, kind of the basic phenomenon has been pretty well worked out, and we understand, what it takes to mitigate charging. And for the most part, I think satellite systems now do pretty well when they're operating in the charging environments, and say like the Earth's outer radiation belt. But occasionally things do still come up, and so there's down here kind of the more recent ones. There's the SOMI MPP had some issues here a number of years ago, and that was thought to be due to charging. 2019 there was a failure of a satellite in GEO, that the failure reports that are available to the public anyway attributed it either to arcing or some sort of a meteoroid impact. And I'm not really clear on that one, whether that really was arcing. It seemed to be a pretty energetic event, and so I don't know, arcing kind of seems a little suspect on that, but that's certainly what has been reported to the public. And sometimes getting your hands on the final investigation reports for these satellites, particularly if they're commercial, is sometimes difficult on that. But the items in red are where ultimately there was a loss emission due to charging. And so, just kind of standing back and looking at this list here, there's quite a few of them. And it's interesting. I think so. One of the first satellite failures that there ever was had to do with electrostatic discharges, and that was one of the early Telstar satellites that was first launched, and the U.S. did some atmospheric nuclear tests that loaded up the radiation belts with charged particles that ultimately caused arcing and failure of the satellite systems. And so, they were arcing failures, but it was a man-made failure ultimately that got the satellites, and not a natural problem. And as I said, the mechanism for these charging anomalies and failures is pretty basic. If you put a satellite, in the space environment, the space isn't empty. There's a low density of charged particles there, and depending on where you're at, they can be quite energetic. So if you're in the Earth's magnetic field, there's trapping mechanisms where the charged particles are trapped for extended periods of time. And when they interact with electromagnetic waves, they can be accelerated to quite high energies. And so when you expose a satellite to those, say, high energy electrons in the Earth's outer radiation belt, you'll build up an excess negative charge on the satellite surface. And so this excess negative charge generates a potential on the surface. And if you have a potential on the spacecraft relative to the local space environment that it's in, that's called the frame potential. That can be a potential threat to noise pulses and things, but generally if it arcs, that just arcs to space. And as long as you don't have any coupling to like sensitive cables or circuits on the surface of the spacecraft, it's probably not much of a threat. The biggest problem is differential charging. And that's where you have a differential potential over the surface of the spacecraft. And when you have that, if it arcs it from one point on the spacecraft, the electric fields between those differential potentials can guide the arc current back to the spacecraft and couple into sensitive circuits or materials and cause quite a bit of damage. So it's really the differential potential that we try to avoid on spacecraft. And these electrostatic discharges occur when the electric fields associated with these potential differences exceed the dielectric breakdown strength of materials, and that allows the charge to flow in an arc. And typically, the dielectric breakdown strengths for materials are on the order of about 10 to the 7 to 10 to the 8 volts per meter for a wide variety of materials. And that's kind of a rule of thumb we use, that when we do charging studies, we we look to see if you get electric fields that approach these values. And I'd say kind of a rule of thumb, you have to be a little careful about that because, in some cases where you have say a flat plane and maybe you're approaching an electric field of 10 to the 7 volts per meter, and you might be half that value, and you're tempted to say, well, it's below the breakdown strength and it's probably safe. If you're just using these kind of generic breakdown strengths, you probably ought to really look up and measure if you don't have a spec sheet from a manufacturer what the actual dielectric breakdown strength is, because you might be surprised. It might be lower than you thought it was. The other problem is if you have sharp edges or protrusions where you have sharp points, and then the local electric field can be enhanced. And it may be that, say like in this flat plate up here on the top right, which was a case where Marshall here was doing some testing on MMOD shields for the space station, and they were getting arcing on this chromic anodized surface here. In this particular case, it was around 60 volts where this was arcing. But it could be that you could get arcing at even lower voltages than that if you had really sharp points or localized enhancements of electric fields. So that's something you have to kind of be careful for. Ultimately, how much damage you get in an arc depends on the energy available in the arc. And that can be estimated from this equation here, which are the energy in an arc is equal to 1/2 the capacitance times the voltage squared. And so, things like this up here again on the right, this chromic acid anodized coating is about 1.3 microns thick. So it's on the order of 10 to the minus 6 meters thick, and if you have 100 volts across that, you have 6, 7, 8. There's 10 to the 8th volts per meter right there, and so you're on the you're on the order of the breakdown strength of some of these materials on that at relatively low voltages, and that very, very thin material then has a high capacitance and can have quite a bit of energy in it, and that's why you get a lot of this arc damage when it does arc. The bottom example down here is a different phenomenon. This is internal charging, and this is where you have energetic electrons. In this case, this was an acrylic block that was charged up by 2 MeV electrons. So they're going to penetrate a few centimeters into this material. And then the people that made this discharge pattern here, they just took a grounded like a nail or a point down here at the bottom, and just tapped it and got a discharge to that point, and all the charge that was distributed here in the outer part of the block then discharged to that point through here. And again, that's not something you want to have happen in your spacecraft components on that. So the anomalies and failures that have to do with charging then depend on the magnitudes of the induced potentials and the strength of the electric fields. They're going to depend on the material configuration and the charge configuration, which ultimately determines the capacitance in that energy equation. And it also is going to depend on the electrical properties of the materials. So things like the surface and volume resistivity and the dielectric constant are important in how much things charge. The secondary and backscattered electron yields are important. We'll talk about those here in a little bit. Photo emission yields are very important, as well as the dielectric breakdown strength. So there's a lot of kind of material science that kind of goes into the understanding of how much things charge, how currents will flow through materials that are charged, and what happens to them if they arc. And so the impacts of charging on the spacecraft systems, includes a variety of things that you really don't want to have happen on your spacecraft. Probably the topmost of these electrostatic discharge currents, these can compromise the functions of sensitive electronics, or they can just be noise pulses, or it could be even a catastrophic damage to the component. You can have a loss of the component. It can cause damage to solar array strings, which can lead to power loss from your photovoltaic systems. You could get uncommanded system states in circuitry that are basically phantom commands, from current pulses in the circuitry. You can get loss of synchronization and timing circuits. You can get spurious mode switching, power on resets of hardware, and erroneous sensor signals. And then finally, you can even get telemetry noise and just loss of data, when you're trying to transmit signals and you get RF noise at the same time, can cause problems in your data transmission depending on the frequencies you're using in your communication systems. So electromagnetic interference can be a problem. You can get EMI noise levels in the receiver band that exceeds the receiver sensitivity. And at that point, your satellite may have a hard time receiving, commands from the ground. Communication issues due to this excess noise, and again, this phantom commands and signals. And then the materials, the arcing on the materials will actually damage materials. So ESD damage to mission critical materials is a problem for satellites. That includes things like thermal control coatings. If you're counting on those surface materials to control the temperature of the spacecraft and it's arcing to the point where it's changing the thermal properties, that's hard on the spacecraft. Re-entry thermal protection systems, you don't want to have arc damage in those. Optical materials such as dielectric coatings on lenses or mirror surfaces can arc, and you need to be, watch that. And the other problem you can get with materials is reattracted outgassing materials. So, if you have chemicals that are outgassing from your spacecraft and they're floating away from the spacecraft, if your spacecraft is charging up and these outgassing products are photoionized, they can be reattracted back to the spacecraft and then deposited on the surface as surface contaminants. And so that's an issue due to charging. And then there's other issues that come up as well. They can certainly compromise science instruments and sensor functions. And I'm going to be showing you some examples today of this modified, what's called an ion line charging signature in the ion spectrum. We use that to monitor charging on a spacecraft, but if you're a space scientist and you want to monitor the ion populations around the spacecraft, these ion line charging signatures are really kind of a problem in your measurements because it's interfering with your measurements. And photoelectron contamination on charged spacecraft is also an issue for if you're trying to measure low energy electrons in the space plasma environment. And then finally, parasitic currents and solar array power losses and just impacts on the power system on photovoltaic systems can be an issue. And I'll show you some examples of that later in the talk. So the potential distributions on the spacecraft surfaces, there's really two fundamental mechanisms that will cause changes in electric potential across a spacecraft. One is electrostatic potentials, and that's due to a net charge density that accumulates on a spacecraft due to plasma currents or photoemission currents. So it's a net current to or from the spacecraft surface. And so these currents, include the plasma currents, the secondary electron currents, photoelectron currents, solar array current collection. If you have active current sources on a spacecraft like electrons or ion beams, electric thrusters, plasma contactors, ion engines, all those sort of things are current sources and can ultimately result in a net accumulation of either positive or negative charge, resulting in a charged spacecraft. The other source of differential potentials on a spacecraft are electrodynamic potentials, and these really aren't charging. What this is it's due to the Lorentz force. So when a spacecraft is moving through a region of space where there's a magnetic field, the V cross B force on the charges in the metal cause the charge to be separated, and the ions go one way and the electrons go the other way. And you get charge separation and you get a net potential, but you haven't really accumulated any net charge. You just redistributed the charge within the conductors on that. But that can be a source of non-trivial electric fields on spacecraft. Typically in low Earth orbit, you can end up with about 0.4 of a volt per meter. For a lot of spacecraft, if your spacecraft's only a few meters in width, the potential difference is, maybe a volt at the most, but and so it's not really that significant. Something like the space station, and again, I'll show you examples of that here in a little bit, because it has scale sizes of about 100 meters across the truss. It actually gets a voltage separation on the order of 40 volts because it's flying, in low Earth orbit across the Earth's magnetic field. On that, probably the worst cases are for spacecrafts in orbit around Jupiter, where the magnetic field is much stronger than the Earth's field, and you can get voltage differences on the order of 600 volts in the Jovian environment at orbital speeds moving through the Jovian magnetic field. And so depending on your destination, these electrodynamic potentials can be significant. So typically when we go to evaluate the charging, what we're looking at is we're trying to account for all the currents that balance on a spacecraft surface, and there's typically models and tools that do that. But if you want to just think about this for a very simple kind of one-dimensional case, and this would be a really simple example here where you got like say a single little patch in space, and you want to look at the current balance to that current little path, and so the charging equation here says that the change of a charge with respect to time is equal to, and then there's different ways you can write this. You can write this in terms of the change of the surface charge density times an area with respect to time, or you can write it in terms of the capacitance times the change in voltage with respect to time. And then that's all equal to the sum of the currents to and from this little patch. And at equilibrium, that's equal to zero, but only at equilibrium. And in a dynamic case, that could actually be non-zero. I mean, you could be accumulating positive or negative charge, and then there's some numerical value here, and it's not zero. And again, there's all these various types of current sources. Incident ions and electrons are just the energetic charged particles in the space plasma environment. Backscattered electrons are electrons that approach the spacecraft surface and then backscatter to space. Conduction currents would be electrons that accumulate in a local region and then conduct away to some other part of the spacecraft. There are secondary electrons where when you get either an ion or electron hits the spacecraft surface and it generates secondary electrons in the materials, and some of those electrons escape to space. And you can have cases where your primary electron may generate 2 or 3 or 4 secondary electrons. And if those all escape to space, you may actually be losing more electrons for each primary electron that approaches the surface. And in a case like that, your electrons actually end up charging the surface positive. And so the secondary currents are a strong control on charging. And we'll see that's particularly important when you get to charging in geo and auroral environments. Photoelectrons, so these would be electrons from the surface that are emitted when a high energy photon, or a photon with energy higher than the work function, hits the surface and emits a photoelectron. And at that point, your surface is now losing electrons to space and is charging positive. And so again, you can have other current sources and beams and thrusters. And so, each one of these currents, can have different signs depending on whether they're collecting ions or electrons or losing ions or electrons. And so ultimately, this charge balance will determine whether the spacecraft's going to charge positive or negative when it comes to equilibrium. One of the simplest things you can look at is just a simple satellite charging in a thermal plasma environment, like in low Earth orbit. This would be an example of kind of what it would look like for space station around 400 kilometers. And so if you just think of like a little spherical spacecraft here, and you got charged particles, in this case, I guess I've written it in terms of a hydrogen plasma. So I have hydrogen ions, protons, and electrons. Although in low Earth orbit, they'd be the oxygen, not protons, and so you get to higher altitudes. But the concept still applies here. And if you want to calculate the mean speed of these particles in the plasma, it's given by this equation here. And so the flux of these particles per unit area crossing a surface is given by this flux equation, where this is the number density of the ions or the electrons. And so alpha is the species, that's either the ions or the electrons, and you multiply it times the number density, and we've assumed here that it's quasi-neutral, and then this is the velocity for the ion or the electron, and so that'll give you the flux to the surface. And typically electrons are more mobile than ions, and so you tend to collect on average more electrons than ions. And so typically in the space plasma environment, then objects will tend to charge slightly negative, because you're collecting more electrons than ions. The electron density is given by this equation, As I said, if we assume the electron flux is equal to the ion flux, and we just set those two values equal to each other, you can solve for the potential that this would come to at equilibrium. And so I've done the calculations here, and it ends up being looking like this in the equation here. So the potential is equal to minus kT times the log of these ratios of the temperatures and the masses and the number densities of the different particle species for the ions and the electrons. And so typically what you get, kT is effectively kind of the energy or the due to the thermal properties of the plasma. And so in a low Earth orbit plasma, where the electron temperature is on the order of about 1/10 of an electron volt, this would be typical for a ISS in the daytime. This potential comes out to be about 1/2 a volt. And so the thermal plasma charging, for low Earth orbit at ISS altitudes, it really isn't all that interesting as far as a concern for a spacecraft. 1/2 a volt is hardly much of a risk for the spacecraft. In the case of space station, their big threat really has to do with the high voltage solar rays. And again, I'll get to that later in the talk today. If you're in the high latitudes, you're going through the auroral zone, you can be going through electron beams that produce the aurora, and they can have these kT energies on the order of 1 kilovolt to 10 kilovolts. And when you do that, you end up with equilibrium potentials on the order of thousands of volts. And so now this is starting to become more significant and more of concern to a spacecraft. If you're out in the Earth's outer radiation belt, the plasma can have energies of tens of kilovolts during geomagnetic storms. And in these situations, you can end up with equilibrium potentials on an object on the order of tens of thousands of volts, tens of kilovolts, and pretty severe potentials. And that's one of the reasons in the early years of satellite operations in GEO, there was a lot of failures on spacecraft, before it was understood that the spacecraft were charging up to these very large values. Now, this particular equation doesn't account for things like secondary electron yields, which would tend to bring these voltages down a bit. And so, to my knowledge, and I'll show you an example here, the worst cases I think that we've seen in GEO are on the order of 10 or 20 kilovolts kind of numbers. I don't think this 55 kilovolts here really is credible. It's an estimate, but the secondary electron yields would probably suppress some of that charging and bring those numbers down a bit. So the secondary electron yields, I've been using this term a bit. As I said, this is a pretty important parameter. And again, this has to do with if you have an electron that hits the surface of a material, and that electron is energetic enough, it will ionize the material, and in doing so, it's producing secondary electrons. And if those secondary electrons are formed near the surface, some fraction of them can escape to space. And so if you are generating more electrons than the single primary electron, and a number of them are escaping, then you can actually be losing more electrons from the surface than the incident electron. And in that particular case, you're going to charge slightly positive. And so that would be the case where you have these secondary electron yields are greater than 1. So you're actually losing more electrons than you're gaining. The region where spacecraft will charge negative is over here on the left, where the electron yields are less than 1. So for very low energy electrons, they aren't producing enough secondaries to really result in much of an electron loss. And so the electron yields are less than 1. But charging here only will charge to maybe a few volts at the most, and so before it comes to equilibrium, and so it isn't much threat to a spacecraft. It's this part of the secondary electron curve over here where you have primary electrons on the order of maybe tens of a kilovolt or more, that when they hit the surface, they're so energetic that they bury deep into the material. And when they produce these secondaries, they're actually deep enough in the material they can't escape. And so you end up not only with the primary, but you have secondary electrons that are trapped within the material. And so you're your net accumulation of electrons now results in a buildup of charge on the spacecraft. And so what we often talk about is the first crossover and the second crossover point, and kind of the energies of where these occur. And you can see the second crossover point is at a few kilovolts. And so you really need to have, you need to have a few kilovolts at least of electrons in the environment in order to result in much charging. And it's been shown over the years that kind of typically the figure of merit is that you really kind of have to have electron temperatures or kind of the average electron energy on the order of about 10 keV before you really see significant charging. And I'll show you some data that confirms that. This equation up here, again, was just these kind of simple one-dimensional charging equations. And what I've done here is I put in a term for the secondary electron, which is just equal to 1 minus delta of the incident electron current. And just to kind of show that the secondary electron yield here is kind of a term that ends up suppressing this current collection because, again, as you're emitting more electrons than you're collecting, it tends to reduce the charging on that. And the two equations on the bottom are just a couple examples of some of the parameterizations that have been used over the years to generate these secondary electron curves. And there's been a lot of work done on kind of the best representations for these curves. And Utah State, I think, recently has done a lot of work on this and have much more sophisticated equations and forms that they use to parameterize secondary yields on materials. Ultimately, when you do analysis for a spacecraft, what most people do is, because it's really not a one-dimensional problem, like I've been kind of showing you in these simple examples, it's really a three-dimensional problem, and you need to account for the current collection not only in a local region on the spacecraft, but also currents on all other regions on the spacecraft and the capacitance, the couples, those regions together on that. And there's been a variety of codes that have been developed over the years to do that. Probably the widest used in the NASA community anyway is this NASCAP 2K code, which is the NASA and Air Force spacecraft analyzer program. And it's been developed over the years. It was a joint program between the Air Force and NASA. And that's pretty widely used still within the U.S. aerospace community for doing charging calculations. There was an earlier version called NASCAP Geo that still floats around and is used a little bit. This NASCAP 2K is export controlled, so it can only be used by U.S. users. The NASCAP Geo code, the older one, was not export controlled. So you'll find some use of it, I think, in the international community who can't get access to the more recent NASCAP 2K. The Space Plasma Interaction System is a European set of codes for spacecraft charging. They have an open source code or an open source model for their code. So any user who wants to use it can get access to the source code and modify it if they want to, which is kind of an interesting approach. And so it's real widely used in the international community, and a lot of people in the United States use it as well. Sparks is a European code. Muscat is a Japanese code that's pretty widely used in Japan. And then, of course, the EMA 3D Charge Plus code that I think there's some sessions during this expo talking about this particular code. Is quickly finding a lot of use in both NASA and the commercial community, in the U.S. and the international community. And, so there's a variety of codes that you can use to attack these problems. All right, let me talk a little bit about some observations on, on charging and just kind of what this looks like and how we know how much things charge up. As I mentioned, this ion line charging signature is kind of a fundamental way that we use data from electrostatic ion analyzers to determine the charge state of a spacecraft. And what's happening here is when you have low energy background ions, so these, maybe a tenth of an eV, thermal plasma ions in the space environment, if your spacecraft charges up to say 1,000 volts, these low energy ions are accelerated to your detector if it's grounded into the frame of the spacecraft, and they'll arrive with an energy. If your spacecraft was 1,000 volts, it'll show up with 1,000 EV, or 1 kilovolt of energy. And so typically the equation that describes the arrival energy, E, that's equal to the initial energy of the ion plus the acceleration you get by the potential on the spacecraft and the charge state of the ion. And typically in low Earth orbit, and I use the case here for DMSP, these are military weather satellites around 800 kilometers. The thermal ion temperatures are typically around an EV. And so, for voltages like this case over here, where it's about 600 volts on the spacecraft, that initial energy of a tenth of an EV is so small compared to the voltage, the accelerated energy of the particle, that we can just neglect E naught. And basically, if we plot these ion energies here in terms of electron volts, we can just read off the energy in this thing that's called the ion line. What that is that's basically the thermal plasma density that's been accelerated up through this potential drop, and it arrives, with this excess energy. And so, in this particular case, the highest value here, in this ion line is about 646 volts, and so that was the potential on the satellite. Or we call it the frame potential, because that's the ground potential of the ground plane relative to the plasma environment. And this electrostatic ion analyzer is grounded into the frame, and so it has the same potential. There is a shift in the electron energy here as well. And so, when you get these features in the spectrum, and that's what I had said before, if you're a space scientist and you're making fundamental measurements of these plasma populations, and you see something like this, you don't like it because it's damaged basically your results are anomalous because of the charging event, has messed up both the ion and the electron data. But for those of us studying charging, we do like this because it makes us easy to read off the potential, in this electrostatic analyzer data. And I put information down here for the DMSP analyzers. They have two instruments they've used over the years. The original one was the SSJ-4, and the current generation satellites use a new instrument called the SSJ-5. But they're both basically capped hemisphere electrostatic analyzers. The electrons measures the electron energies over 20 channels from a range from about 30 electron volts to 30 keV, and the ions in about 20 channels from 30 EV to 30 keV. And I put down here the channel number and the energy of the center of each channel. And so fundamentally, we can estimate these potentials kind of to the resolution that's available, in these energy bands here. So for instance, the 646, that peak shows up in the 8th energy channel. It didn't show up in the 9th, so it didn't charge up to 949 volts, but it was at least 646 volts. And there's some uncertainty here because the width on these channels, each one of them, delta E over E, is about 9%. So there's kind of on the order of a 9% error here, in the voltage that we're reading off from these ion lines here. And I should mention, these are just the kind of the nominal energies that the Air Force reports for these instruments that are kind of widely used for initial estimates. If you really get serious about this, you really have to go back and get the calibration data, from each instrument, and each satellite will have a different set of numbers. They'll be pretty close to these values, but not exactly the same. So this is real typical how we get information on charging, and the DMSP satellites have been a really big source of charging information over the years. For geosurface charging, you could actually charge up quite a bit. This plot on the left is a figure that NOAA put together a number of years ago. And what it's intended to show, you're looking down on the ecliptic plane from above the Earth. So this would be looking down on the Earth's North Pole. And so the sun would be on the left and the Earth's magnetotail would be on the right. And so this would be the dawn sector and the dusk sector. And there's a phenomenon where plasma injected from the tail was driven in towards the Earth will be charge will be separated because there's forces on the there's forces on the plasma. It has to do with the grad B and the curvature drifts of the plasma, and so the electrons go eastward into the dawn sector, and the ions go westward into the dusk sector. And so this region over here in space, kind of between midnight and dawn, typically will have an excess of a hot negative charge from plasma in this region. And so that's a place where we typically see surface charging on spacecraft during geomagnetic storms. And they've plotted here at kind of at the distance of GEO down here, these little black dots are locations where they've seen anomalies on the GOES spacecraft. Back in this case, it was the GOES 4 and GOES 5 spacecraft from a number of years ago. And I think these are phantom commands in the electronic systems. And again, you can see those tend to peak kind of in this same midnight to dawn sector where the hot plasma is. Now, there are a few out here, in the day side or even kind of in the post-noon sector. And I suppose it's possible this could be some localized surface charging. They could also be due to internal charging for radiation belt electrons, since GEO is out on the outer edge of the outer radiation belt. On that, it's kind of hard to tell from this figure. This figure on the right kind of shows an example of again, electrostatic analyzer data. This is from the Applied Technology Satellite, or ATS-6. This is from the mid-1970s. And I like to show this one because it kind of shows you how long people have been looking at, charging phenomenon and the risk to satellites. And in this particular case, the time is on the horizontal axis for the electrons in the top panel here. The energy goes from the bottom to the top. But for the bottom panel here, for the ions, they've inverted it. So that way that puts the low energy ions and the electrons together near the center of the plot. So it's getting more energetic as you go down for the ions. So this is the ion charging line here. And this region in here, whether you don't see anything, that's because all that thermal plasma has been accelerated up to the spacecraft potential, and there just isn't anything lower energy than below that, because it's all been accelerated to that higher energy. And in this particular case, this I think was the largest charging event ever recorded for ATS-6. It was about 19 kilovolts. And I have heard rumors that during this ATS 5 or 6 program that they had seen a potential at one point of 28 kilovolts, but I've never been actually able to find the data or confirm that. And so I'm still trying to looking for a source that can confirm that, if that's true. This is another example. These are from Los Alamos satellites that are operating in geostationary orbit. I think these are used for for a nuclear surveillance system, looking for nuclear weapons tests in the world and a variety of other DoD applications. But they also have a really nice set of plasma instruments on it that have been very useful over the years for research studies of charging and charged particle physics in the outer radiation belt. So over here on the left is an example with no charging. This little feature in here is down around an energy of about 1 eV. This is actually the extension of the Earth's plasmasphere out to geostationary orbit. And down here, this is the ion panel up on the top. And so the format again is time on the horizontal axis. In this particular one, they have energies going from the bottom to the top for both the ions on the top and the electrons here on the bottom. And in this particular case, this feature, those are photoelectrons at very low energies. Again, this is down less than an electron volt, so very, very low energies. These populations up here are between about 1 and 10 kilovolts, and so these are the hot plasmas from geomagnetic storms in the outer plasma environment. But in this particular case, it wasn't really energetic enough to cause any charging, and so if you look up here in the ion spectrum, you don't really see any ion line up there. This case on the right is different. Now you see the ion line up here. And so there's charging. In this particular case, it's charging to almost 8 kilovolts when it's in eclipse. And this little triangle here at the bottom of the plots is marking local midnight. And these photoelectrons, if you kind of see here, they go away right around midnight, and that's because for this in March, the satellite is going through eclipse, and so you get strong photoelectrons over a lot of the day, but when you're behind the Earth in the eclipse condition during eclipse season in GEO, then there's no photoelectrons there, and because there's no photoelectrons, that doesn't suppress the charging, and you can charge up to these very large levels, these kilovolt levels. Once you come out of eclipse, into sunlight, then the charging drops. So this ion line up here drops from 8 kilovolts down to, perhaps just a kilovolt, or even under, less than a kilovolt or so down there. So again, this is a particularly useful set of data. These satellites have been operational in for many decades in GEO. So there's tons of data from these to analyze, for charging situations. More recently, NASA, launched the Van Allen probe spacecraft, and there was 2 spacecraft, Van Allen probes A and B, and these were on geostationary transfer orbit. So they went almost all the way out to geostationary orbit, and they came back within about 350 kilometers above the Earth. And so they were, cutting across magnetic field lines to study both the inner and outer radiation belts. Yeah, but they would occasionally see surface charging events. And this is an example here. This is on the HOPE instrument. And so HOPE measures electrons. This is the bottom colored panel. It also measured separately oxygen, helium, and hydrogen ions. And then the very bottom panel down here is the radial distance from the Earth in terms of L value. And so this would be kind of, you could think of it as the radial distance to the apex of a geomagnetic field line near the equator. And so as you're out near the L equals 6, which is pretty close to GEO, you're in these really hot plasma environments where you have a lot of high energy electrons and ions, and you can see this ion charging line. And it shows up not only in the hydrogen, but it shows up here in the helium and in the oxygen as well. And in this particular case, there's an example in one orbit, and it was seen again on the next orbit. In fact, it was more pronounced on the second orbit. But the peak here was only around 100 or 200 volts negative. So it wasn't a terrifically strong charging event, but you do see it over a good appreciable fraction of the orbit as it's passing through the outer radiation belt. This is another example. This one's from the Van Allen probe B satellite, and in a very similar orbit. And this particular case. There's a charging here that charged up to about 2 kilovolts, so more severe charging, and that was because the electrons here reached a much higher energy level. They're more energetic, and so they drive stronger charging. A phenomenon of importance for charging in GEO, and in particular has to do with there's a threshold condition that you have to watch for, and that has to do. It's been talked about in terms of temperatures over the years, or kind of energy metrics, and ultimately this has to do again with the secondary electron yield, and so that's why I put the plot down here again, and again with the secondary crossover point. Until you have an appreciable fraction of electrons with energies above the secondary crossover point, most of the yields where the electrons are hitting the surface are going to be greater than 1. But once you get most of your plasma out here, where your electrons or the secondary yields are less than 1, that's where you start accumulating charge. And so you'll see that when you look at data. So this plot here in the upper center is some examples from 2 satellites. This ATS-6, that's the Applied Technology Satellite 6, and SCATHA was an early research satellite that the Air Force put together to look at charging in GEO. And you can see for a wide range of electron energies, the voltages on the satellite are very small, or even slightly positive. And so there's no appreciable charging, but once you reach some kind of critical energy here, then they quickly start charging up. And that critical energy here is somewhere around 10 kilovolts. And again, that's because by the time you get up here to about 10 kilovolts, then the secondary yields are so low that you're not really losing enough electrons through the secondary electron yield process to suppress the charging. And the same sort of thing shows up in the LANL data. In this particular case, and I'm sorry, I should have mentioned here, the spacecraft potential becomes more negative as you go down the plot, and that's plotted against this electron transition energy. You can kind of think of that as a temperature or kind of the average electron energy on that. And that's why, this is very little charging up here and then much more negative charging down here. The plot on the bottom, again, is the electron temperature on the horizontal axis, but now the spacecraft potential becomes increasingly negative as you go up the scale. And again, you can see here that for a range of electron temperatures, you don't really have much charging at all. And it isn't until you get up to, maybe, 2 or 3 keV on the electron temperatures that you start seeing charging. And you don't get this, significant charging of these very large energies or very large potentials till you get temperatures, on the order of, 5 to 10 keV, kind of for these, really, really big values out here. And you can see that again in the ATS-6 data. This is an example from 4th of October, 1974. And so the electrons are on the top and the ions are on the bottom. And again, remember this ion energy is inverted here. And so, as we come along and you go into eclipse, not only these are photoelectrons here when you're in sunlight, but once you go into eclipse, you lose those photoelectrons. And then also at the same time, there was a plasma injection event that the electron energy drifted up to a little higher energies. And because there was no photo emission and you get hotter background plasma, then you start charging. And you can see that in terms of the ion line here. In this particular case, it charged to about a kilovolt negative. And then once you came out of the eclipse back into sunlight, you can see the photoelectrons show up again. The photoelectrons then tend to suppress the charging. And there might be a little bit of drop here in the highest energy electrons, and that pretty quickly then drops, suppresses the charging on that. And if you look at that in terms of just time series of electron temperatures and spacecraft potentials, this is a data set. Sorry, I guess I don't have. Oh, yeah, this is from Shulai's in 2008 study that he had put together. And so he always talked about in terms of these critical temperatures. And basically, he looked at the electron temperatures and tried to see at what temperatures charging would start. And what you can see here is you come along, you get variations in electron temperature. But it isn't until those values, across some critical threshold, you start seeing charging. And this bottom panel here that's supposed to show spacecraft charging, these numbers get, big. The further down the plot you go, the more negative potentials. And you can kind of see, like this case here, for instance, that it's approaching maybe 3 volts. And I'm thinking those should be kilovolts, not volts. But you get these larger negative potentials here, but you don't get these negative potentials until those temperatures have become hotter than some critical threshold. And again, that has to do with those secondary electron yields. And those critical temperatures ultimately are a material property because the secondary electron yields are a material property. And so you can keep track of these things, for a variety of materials that would be used in spacecraft construction. And that would tell you then, how susceptible a particular material might be to charging because of these secondary electron yields and this, charging onset. You can also get positive charging in sunlight in GEO, and this is kind of an interesting phenomenon because if you think about the plasma in GEO, which is typically this hot plasma, and you should, typically you should be collecting negative electrons, in excess of electrons more often, and you should always be charging negative. But it turns out there are cases where the photo emission isn't strong enough to eliminate surface charging. And particularly if you have a really low plasma density, that photo emission can actually well, typically photo emission should suppress the charging, but if you have these dielectrics in sunlight, you can have a case where you get these barrier potentials that form on a satellite. And so this is a lot of it. This is just a simulation where there's a spherical satellite and looking at the potential structure around the satellite. And if you're forming, you're emitting photoelectrons on the sun side of the spacecraft, they can be trapped within these barrier potentials, and you basically have a case where even though you're emitting photoelectrons, they can't escape the surface. You can still get negative charging in sunlight. And that's the origin of this secondary curve that shows up in this Los Alamos data down here for negative charging in sunlight. Auroral charging is an interesting phenomenon. This is one of my favorites. Satellites that pass through in low Earth orbit that are in polar orbits, and they'll pass through auroral arcs at high latitudes. And when they can charge up, when the electron flux is dominated again by these high energy electrons, if there's some, around 10 keV electrons or more, and it's not that 10 keV isn't a hard number, probably 8 or 9 or 10, 8 or 9, 10 keV would probably do it. It could be 14 keV, but whatever it is, it needs to be higher than, again, this threshold value here needs to be kind of over in this region of the secondary electron yield curve, well away from that secondary crossover point in order to really see, charge accumulation starting to build up. And because of this, auroral charging is real strongly controlled by the type of aurora that the spacecraft is exposed to. And so it depends on the energy of the primary electrons and the secondary electron yields. It also depends on the density of the ambient plasma. And that's because if you have a background plasma, it can balance the auroral electron collection and ultimately suppress the charging. But it's interesting when you look at aurora. So like this case on the top right up here, a beautiful picture of a really pretty strong aurora. But basically all this green up here, that's atomic oxygen emissions from probably 120 kilometers and above. And so, the energies of the electrons that are responsible for that kind of aurora typically don't exceed maybe a few kilovolts. And so they typically would probably be down, in this part of the region of the secondary electron curve. So satellites going through an aurora like this one on the top right up here probably wouldn't charge a negative at all. Or if anything, they could even charge slightly positive. It's this kind of aurora in the bottom right where you get these really strong pink lower borders that we think are associated with a strong auroral charging. And that's because in order to get this kind of a pink at the lower part here, this is when you have an appreciable population of these 10 keV electrons in the aurora, and they're penetrating to altitudes maybe 80 or 90 kilometers in the atmosphere, very deep in the atmosphere, down to where there's a lot of diatomic oxygen and nitrogen. And so you're getting this pink color from the diatomic species that are being emitted at lower altitudes. And so you typically, in order to get these things, you need to have very, very, very strong auroral acceleration and high energy electron events. And I'll show you some more examples here of charging events where you can see that in the DMSP data sets. The other thing that's interesting about auroral charging is there's a strong dependence on solar cycle that's been studied over the years. And there's been a couple of sets of papers, and I've just referenced 3 here. I think there's some of the more important ones that have shown this strong dependence of auroral charging on solar cycle. And what's interesting about it is that auroral charging tends to happen more often during solar minimum and not solar maximum, which seems kind of counterintuitive, that you think, during solar maximum, you'd have a lot more geomagnetic storms. You should have a lot more charging. But there's a set of conditions that have to be true in order for auroral charging to occur. That have been, and this was discovered again many years ago in the mid-1980s, and it was shown that for the DMSP satellites, in order to get significant charging to perhaps 100 volts or more negative, that the spacecraft had to be in darkness, and if there was any photo emission, that it basically suppressed the charging for the DMSP satellites. The thermal plasma density or background plasma density had to be less than 10 to the 4 volts per cubic centimeter. If it was much higher than that, then there was just too much background plasma density, and that would tend to suppress the charging. And then the integral number flux of these energetic auroral electrons had to be of energies greater than 10 keV, had to be in, at least about 10 to the 8 electrons per square centimeter per second per steradian. So you had to have a really strong beam, current of electrons in that auroral acceleration event. And if any of these are not true, then the auroral charging won't occur. And so, it's been shown over the years. This top plot up here is from a paper by Anderson and colleagues showing that there's over a solar cycle. So this starts in 1989 to 2001. He's plotted densities from the DMSP satellites. The blue is the northern hemisphere and red is the southern hemisphere. And you can see that during solar maximum, and I can tell a solar maximum, the bottom panel down here, the sunspot number is this dotted line. So this is solar maximum, solar minimum, solar maximum. So during the solar maximum conditions, that density is higher than that 10 to the 4 threshold. And I put a green line here to mark that threshold. And so you don't really expect to see auroral charging under these conditions because that background plasma density is too high. And so these solid black lines down here in the bottom are a record of event frequency for auroral charging in the DMSP satellites from this study that Anderson put together in 2012. And so you can see that there's very few or no charging down here during solar maximum. Most of the charging events occur during solar minimum. And in those conditions, you can find conditions depending on the season where the plasma density is low enough that you meet the threshold criteria for the background plasma density. And typically this only happens in the winter hemisphere around the local solstice. So southern hemisphere around the summer, and northern hemisphere in the winter around the solstice periods do you see significant charging. And that's kind of what the plot down here is Anderson's statistics, showing this seasonal effect in the charging events. Now, I will warn you, and I'll show you a reason why here in a moment. Designers for low Earth orbit polar missions might assume that they can just ignore charging and implementing charging mitigation designs in their spacecraft if they're only going to be operating during solar maximum conditions. And over the years, we've got a lot of people who've asked that question. If they're going to build a satellite and they're only going to launch and be operational for, say, right now we're at solar maximum, they're only going to be operational for a year or two. Why do they need to worry about charging? And I'll show you in a moment that that's probably not such a good thing to assume. That at the very least, a lot of times you don't really know exactly when you're going to launch anyway. Your schedule might slip so much that you might think you're going to launch at solar maximum and you might end up launching at solar minimum. So it's probably a better idea to design for it. But it also turns out that we have seen charging even during solar maximum if the solar activity is low enough. And so I'll show you that here in a moment. Just at first, I got a couple examples here of auroral charging from a couple of different cases. And so this is one here again where the DMSP spacecraft, get my cursor, yeah, here we go, my cursor. And so you can see the ion line here. And so the peak charging here is up to about 400 volts negative on this particular case. In the electron panel down here, you can see that the electron energies go up to actually that kind of that topmost energy channel. In fact, it even probably goes off scale. So there's probably more energetic electrons here than the electron analyzer can even measure in this particular case. And this is a phenomenon we call an inverted V because it kind of looks like an upside down V. This is another example of one over here, an inverted V, just a lower energy. But a particularly high flux through that, and you can see during this one you get charging over here, but not as much as you got over here because the energy is quite a bit more up here. So it's really these inverted V's that are the the phenomenon that drive auroral charging. And that's, again, where, you get a lot of electrons. The spectrum is dominated by these really high energy tens of keV electrons that penetrate deep in the atmosphere and would give rise to that, those auroral forms with the pink lower borders that I showed you before. Some of these cases over here on the right actually have much higher flux, more electrons per square centimeter per second in them than this event up here. Excuse me. But you don't see any charging that goes along with that, and that's because these electrons here are all about a kilovolt or less in energy. And again, the secondary yields there would suppress charging. So you just don't get any charging there. And this particular case here, where you got the charging, is because this topmost electron energy in this inverted V was up at a high enough energy that it probably was far enough away from that second crossover point. Here's another example. This is from DMSP. This is charging to about 1400 volts negative. And yeah, I didn't do a very good job on the line there, but looks like, this line here, I think, makes it up just a little over 1 kilovolt here on the energy. And so it's in that 1400 volt channel. And so, again, you can see the variations in the potential over time and kind of the variations in the energy of the electrons that gave rise to that. And this is pretty typical for these charging events. You get the highest voltage may only last for a second or two. I should have mentioned to you, each one of these electron spectra in this panel are about 1 second apart. And so each pixel here represents a 1 second electron spectrum on that. So in this particular case, it reached 1400 volts negative, but it was only there for a second. And it pretty quickly it arose to that potential and then decreased, after it flew through that, this auroral arc here that caused that strong charging. And I think, yeah, this is the one where I'm showing an example from solar maximum auroral charging. So here's another charging event here, where the maximum up here, again, is around 1 kilovolt. In this particular case, this was from July of 2012. And in this particular case, this was, I've marked it here on the plot. This is the F107 index. So this is a measure of solar activity. And in this particular case, it's a radio emission that correlates with ultraviolet light from the sun. And so this is from 2008 to 2020. So this is the last solar cycle. This is solar cycle 24. We're currently in 25. But solar cycle 24 was a double peak cycle. The first peak was lower than the second peak of the cycle. And this particular event, I've marked the location and time in blue. And so it's in this kind of lower activity peak of first peak of the cycle. And in this particular case, the solar activity was low enough that the background plasma density, and that shows up over here in this bottom right panel. So the primary density, the dotted line here is the 10 to the 4, and the measured potential is down around 10 to the 3. And so we have a background plasma density of 10 to the 3. We have an electron currents on the order of 10 to the 8, 10 to the 9 per square centimeter per second per steradian for these energetic electrons. And it's in darkness, so that meets all 3 criteria for auroral charging. And in fact, that's what we see as an auroral charging event, even though this was near the peak, that first peak of solar cycle 24. And so that's why I say it's probably not a good idea to assume that the conditions are going to be such that you won't see auroral charging during the peak of the solar cycle, even though the conditions in the past had shown that. And I think that's because when a lot of those early studies were done, the solar cycles were much stronger, and the peak activity was much stronger, and it would lead to, it would suppress the charging much more than the more recent solar cycles are doing. Let's see, auroral charging. We also see on space station. This is an interesting example. I'm going to kind of use this as a segue into charging on space station and other satellites having to do with solar ray charging. But I want to show you this auroral charging case first, because this is to date, to my knowledge, is the biggest charging event we've seen on space station due to Aurora, and it's only about 17 volts negative, or more negative kind of than the background charging on station. So it's not very much. And station's at about 400 kilometers. And in this particular case, station kind of went through the edge of the auroral zone. It kind of just nicked the edge of the auroral zone. In the bottom panel here, in the bottom right, these are electron greater than 30 kilovolt electrons from the NOAA POSE satellites. And the L value that space station was at when it saw the charging event was at about between 5 and 6. And it was during a case here where there's some pretty strong electron precipitation of these greater than 30 kilovolt electrons. And so we think that that's a case of auroral charging on the International Space Station. And I think this was one of the first ones we ever saw. But over the years, we have seen quite a few of these. It's not unusual when you get a geomagnetic storm and the aurora moves equatorward that it makes it down to station orbit, and we'll start seeing these things. And we'll get data sets that look like this. So this is a case here. I think this is probably the one that I just showed you. Let's see, is that right? 9th of March. No, I'm sorry, it was a different one. So this is a different one here, but these are all cases of auroral charging, and we get these kind of ratty potentials down here in the southern hemisphere, and that's cases of auroral charging. The overall variations have to do with the E cross B and that those inductive potentials. And I'll show you a better example of that here in a moment. But what I really want to focus on is in these far southern hemisphere regions where we're seeing these kind of strong peaks and noisy data. Right here where I've got the this pink bar, we actually have some data from a space station where the crew was taking some pictures, and you can see that they're in the cupola, and this is a window or an observatory in the space station that looks down from the station towards Earth. And they had a camera set up, and so these are just 3 separate images during that time period that I just showed you, which was pretty close to the measurement of where we saw some of those charging peaks. And you can see this green light down here is the aurora below space station. So we know the space station is passing through these auroral arcs. At the time that we see, these changes in the potential on space station, kind of confirms that there's aurora present at the time there's charging. Unfortunately, we don't have any plasma instruments capable of measuring the auroral electrons on station that we could use to confirm that. So that's why we had to use these image data to do that. So I'm going to move now to solar array charging. And as I said, that for space station, it's kind of interesting. I mean, we do see auroral charging, but the strongest charging we see on station is not due to aurora. It actually is due to the plasma interaction and with the photovoltaic system that provides power on station, and that's because a station has a high voltage system. And so, in general, if you have a spacecraft with a photovoltaic array and it's grounded to a vehicle on the negative end of the array, and that's the situation I've drawn here in this cartoon. So you have a solar array, and your voltage range across the solar array goes from 0 volts to some voltage I just called S. That typically at equilibrium, part of it'll collect electrons and ions over the solar array, such that some small fraction of the solar array will collect electrons because they're more mobile, and a much larger area of the array will collect ions because they're less mobile. And that comes to equilibrium with the spacecraft potential, then about 90% of the string voltage across the array. And that's just kind of in general terms. So if you had a 100-volt solar array, you might expect to see charging on the spacecraft to 90 volts negative due to the current collection from the plasma on this. And so that's just in general. And if you have 30-volt solar arrays, a lot of U.S. satellites use these 28-volt buses. And so for those, this kind of charging really doesn't matter that much at all. It might be a nuisance to some of the scientific instruments on it, but it's not an engineering problem to the operation of the satellite. And I mean, typically, it only really is an issue when you have high voltage systems with a few hundred volts or negative or more. And the issue really becomes one, you can get arcing on the satellite when the string voltages exceed about 200 volts on that. So for really high voltage systems, this arcing and current collection can be an issue on this. But we can see this on space station and some other satellites. And the first example I'm going to show you here is a case from the UR satellite. This is the Upper Atmospheric Research Satellite. This was a NASA and Southwest Research Institute program that operated from 1991 to 2005 when it was decommissioned. And it was in about a 575-kilometer orbit and about 57 degrees inclination. And this is a plot here, again, from their electrostatic ion analyzer. And so time on the horizontal axis, the electron energy on the ion energy on the vertical axis measured in electron volts. And so they've color-coded the flux. And you can see when they come into sunlight and the arrays are biased, you get this ion line that jumps. And it stays at a fairly high value here and then drops after a period of time. I think when it goes back into eclipse, and then this is the coming back out in the next orbit. And in this particular case, they regularly saw charging at eclipse exit to about 90 volts negative. Because the photovoltaic arrays were typically about 100 volts string voltage when they were cold and about 75 volts when they were warm. And again, it's not necessarily a problem for the satellite per se, but in this particular case, if you're counting on this data for analyzing the ion environments in low Earth orbit, your data is compromised by the potential on the satellite. And actually, for this reason, a lot of the early research satellites that the U.S. used in low Earth orbit, they would either ground them on the positive end of the array, or they would use floating grounds, and the current collection on the array was decoupled from the satellite, the voltage on the satellite itself, to avoid this problem. This is another example. This is the Horyu-2 satellite. This was built and flown by JAXA and the Kyushu Institute of Technology. And this one started in 2012. It was in about a 650 to 670 kilometer orbit in about 98 degrees, so about sun synchronous orbit. They had a test circuit on here on some of these solar arrays that would go up to 350 volts on the solar arrays. And in this particular case, when they come into sunlight, the generation voltage that in red, that's the voltage of the strings on the cells when it's biased in sunlight. And the blue is the potential on the spacecraft bus. And you can see that it's tracking pretty closely to the generation voltage. And again, they were seeing, for the 350 volt solar arrays, they were seeing eclipse exits, the charging over 300 volts negative on that. So quite strong charging, on this research satellite. And then the ones I'm going to show you now, this all comes from the space station program. We get, as I said before, we kind of get two forms of potential variations, and this shows up really clearly on the space station data. So when you look at potential measurements, and that's what I have in the top plot here, it oscillates, and that's because that's the V cross B dot L. That's the inductive potential. That has to do with the motion of the vehicle across the geomagnetic field lines. But then this black and yellow, I've marked when it's in sunlight and when it's in darkness. So black is darkness and yellow is in sunlight. And every time we come into sunlight, the potential becomes more negative. And that's when the arrays turn on when you come into sunlight and start collecting current. And so we get these photovoltaic charging peaks every time we enter sunlight on it. And so there's, again, there's two sources of variation here in the voltages. One is this inductive and the other is current collection on that. And this is kind of typical for station. Maybe we would see 20 to 30 volts negative kind of on a routine basis for most of this current collection. And typically we get the strong peaks right after sunlight. We come into sunlight for a period of time, and the rays would track the sunlight, and they would collect current as long as they needed to top off the batteries. But once they would started topping off the batteries, then they would start dropping strings out of the current collection. They would shunt them, and they essentially short the strings when they don't need the power. And so some of this, what you see, it's negative for a period of time, and then it drops pretty quickly. That's because they start to, they didn't need all that excess power. They was pretty quickly topped off the power, and they start dropping strings on that. The case when you come into sunlight, actually, it's a dynamic problem. That cartoon I showed you before was kind of an equilibrium solution, where just to show that how you might get upwards of 90% of the string potential. But in the case of space station, when you come into sunlight, it's a dynamic process. So when you first come into sunlight, you have a unbiased arrays and in darkness, so there's no voltage across the solar rays, and so the structure potential is maybe, again, fractions of a volt or a volt negative at the most, just from collecting thermal plasma, but not very much charging at all. And really, the V cross B is dominant over most of the orbit, and that's where you see most of the changes in potential. But once you come into sunlight, and you get a bias across the arrays on the U.S. sector, these high voltage arrays have 160 volt strings, and so you get a full 160 volts across the arrays. And when you first come into sunlight, most of that array is positive with respect to the plasma environment. And so you're collecting electrons over the whole array, and it quickly starts collecting current, and the voltage on the spacecraft bus is dropping. And that'll happen for some period of time until something happens to, either comes into equilibrium or charging is reduced through some process, either through power regulation, where you shunt the arrays, or you short the arrays because you don't need the power, or you have something. A PCU is a plasma contactor unit. That's a unit on station that actually discharges excess charge, so that would return the potential to a lower value. You can get it by rotating the arrays, which will reduce the current collection on the arrays, or arcing. If you get arcs, it can actually do it. And we've seen over the years, there's all these examples of modifying the potential on station. And so just a quick example here, kind of three broad categories of charging we've seen on station over the years due to the high voltage solar arrays. One type we call normal charging, and that's this case here where you come into sunlight and it kind of charges negative to maybe 20 or 30 volts negative for, some tens of minutes or so. And then as they start shunting the strings, because they don't need all the excess power, then that voltage drops. The other thing that's happening here is, in addition to the shunting, when you first come into sunlight, the arrays are pretty much pointed, straight on, looking at the sun. And so you get kind of maximum current collection on the arrays. But of course, over time, as you're moving around to the kind of the noon segment of the orbit or into the afternoon, the arrays are tracking the sun, and so they're rotating. And by the time you hit this noon sector here, the arrays are probably pointed 90 degrees from the RAM, and so that cuts off a lot of the current collection on the solar arrays. So again, there's various physical processes there that limit the charging to this morning part of the orbit here. Occasionally, we would see this phenomenon that we call rapid charging events, and that's when you come into sunlight and you'll get charging upwards of maybe 60 or 70 volts negative for a short period of time. And they're never very long. They're typically only, a number of seconds wide, and at the very largest voltage, just a few seconds wide on that. And we think that has to do with, it's a phenomenon that has to do with low plasma densities, because you don't have enough plasma current and to kind of control the charging. And when you basically come into sunlight with this full string voltage in full sunlight, and you're just sucking in electrons over the entire array, so it quickly charges negative before it finally comes into equilibrium and controls the potential. Then on other cases, we did some experiments back in 2010 where we got these really large charging peaks here that were down around 80 or 90 or even pushing 100 volts negative. And I show you these are kind of interesting because originally there was estimates the station potentials could be as much as 120 or 130 volts negative. If you use that kind of 90% of the string array figure of merit. And of course, when station was launched, we never saw those kind of numbers. And it turns out there's a lot more ion collection area on station than people had recognized in the early years when they were doing the early assessments. And so So it kind of, controlled a lot of the charging, these lower values, but we have seen cases where we got these really large ones. And these were cases where we did experiments where we had them turn the power off on the solar arrays until we were a full 3 minutes into the sunlight, and then they turned on the arrays. And at that point, you basically turn the arrays on, you completely bias them, in full sunlight, and the entire array is now an electron collector. And I'm going to zoom in on that region I have marked down there, and what you see here is actually 8 different peaks, and every one of these is associated with one of the arrays on station. So there's 8 arrays, and they're numerically labeled 1A, 1B, 2A, 2B, all the various strings. And when we had them do this experiment, they basically, we assume that they turn them all on at once, but they don't do it that way. They do them sequentially, and they did them about a second apart. And so you can see these charging peaks. As you quickly collect electron currents as a string or array 1A is turned on, and then it comes to equilibrium. Then the next one's turned on, it comes to equilibrium. And as you work your way down to more and more of these, you can see this baseline level is becoming more and more negative as you get more and more electron collection, as each array is turned on in sunlight. On that. So this data is all from an instrument called the FPMU. This is the Floating Potential Measurement Unit on space station. And it's been on station since August of 2006, and it's provided a lot of insight into the plasma interactions with these high voltage solar arrays on the space station. And just a quick note here, some of the statistics of potentials on station. This is the plot over here on the right, just shows a scatter plot. These are the centerline potentials. So we've taken the voltage at the location of the FPMU, and then it's been adjusted to the center line of the space station to remove the V cross B, from those inductive potentials, and then just plotted as a function of time. And these are just the eclipse exit peak negative values from each orbit. And you can see there's a nice solar cycle of dependence here. So again, this is the last solar cycle, cycle 24 here. And down for these solar minimum periods is where we see some of these bigger negative potentials. And these are all from these rapid charging events. As I said before, these typically occur in low density plasma environments. And there's a phenomenon of kind of these equatorial plasma holes that form an eclipse exit. Where these things are occurring, so there is a dependence on solar cycle for this phenomenon. See, I guess I'm starting to run out of time here. Let me move through a couple of these here pretty quickly. Just a couple other examples of interest. If you move into the outer solar system or even go into interplanetary space, the plasma densities actually get low enough that the current collection from the plasma isn't the dominant charging process. It's actually photo emission is the dominant charging process. And in those cases, then spacecraft will charge positive. And you can see that in terms of the photoelectrons that show up in the electron spectra on electron instruments. And so that's what I'm showing you here on the right. This is from the GeoTail spacecraft. And so this was a case where a GeoTail was operating in the magnetotail, where the photo emission was dominating over the plasma current. And you can kind of see there's an edge here on these higher fluxes of electrons. And that's because the photoelectrons have a spectrum, and high enough energies that are beyond the potential of the spacecraft can escape, but ones with less energy than the potential of the spacecraft are trapped. And so you can just read off the spacecraft potential, from the edge of this current here. I mean, the edge of the spectrum. And they also have an instrument on the spacecraft that you can read it off directly. And so it's about 30 volts, and that corresponds with kind of the edge up here of those photo emissions. The spacecraft went from the magnetosheath into the magnetosphere, and as it passed through the plasma sheet, there was a lot more hot electrons in the environment. In that particular case, the hot electrons would then start charging it less positive or more negative, if you want to think about it that way. It wasn't enough to actually drive the potential completely negative, but it did suppress the positive charging. And you can see the drop in kind of the edge of these photoelectrons there, and also down in this bottom panel, the drop in the spacecraft potential. And so, again, photo emission kind of coupled with plasma environments in the outer magnetosphere or interplanetary space can cause some interesting phenomenon on kind of positive charging on the spacecraft. And this is another example. This is from the cluster spacecraft. In this particular case, it was outbound from the magnetosheath into the solar wind. And so the energy of the electrons in this top panel up here, these are photoelectrons, the lowest energies, and there's a sharp cutoff. And again, the photoelectrons with higher energies were just lost to space, and the ones with lower energies are trapped. And again, you can use that to read off basically the potential on the spacecraft. And then it's at this vertical red line here, it went from the magnetosheath through the bow shock and out into the solar wind. And once it was in the solar wind, then the currents from the high energy plasma were much lower, and it became that you were trapping more of the photoelectrons, and you can see that the positive potential becomes bigger, in that particular case. Again, this is not an issue of a threat to a spacecraft or anything. These values are so low on these voltages, but certainly, if you're a scientist and you're interested in studying low energy plasma environments, this data is a problem for you. And I'm just going to go through, I have a couple quick charts here to go through and finish up today, talking about internal and or deep dielectric charging. Again, this is the case where you have high energy electrons, maybe some 100 kilovolts or more, and they penetrate spacecraft walls and accumulate dielectrics or isolated conductors. And the threat here really is energetic electrons with sufficient flux to charge circuit boards and cable insulation and ungrounded metal faster than the charge can dissipate. And if you're accumulating charge density and you generate an electric field in excess of the breakdown strength, resulting in electrostatic discharge, and that's inside of your spacecraft, and this can be inside the Faraday cage that's supposed to protect the spacecraft from radio frequency noise. You're having arcing kind of on the circuits or the actual components that are running your spacecraft, and this can be a really serious problem for spacecraft on that. So this figure on the right is that same example of one of those acrylic blocks charged by 2 to 5 MeV electrons. One of the interesting things about internal charging anomalies is they tend to peak actually in the descending phase of the solar cycle, and which we're actually kind of getting ready to go into now. We're right at solar maximum, and so this is from a number of years ago, but we're kind of at this corresponding point in the solar cycle here, and over the next few years we'll be looking at this descending phase of the cycle. And this plot, what they've plotted here is the days in a 27-day solar rotation cycle on the vertical axis, the years on the horizontal axis. And so these areas which are yellow or red are areas where there's high fluences of greater than 2 MeV electrons over a 2-day period. And then the little black dots are times when there was phantom commands in the GOES spacecraft. And you can see they tend to correlate when there's these high fluences of greater than 2 MeV electrons. And the problem tends to be more common again in this descending phase of the solar cycle. And in fact, over here, kind of during the peak of the solar cycle, there really wasn't much of a problem at all. And I think the reason for that is because during the peak of the solar cycle, you get a lot of CME-driven storms that have electric fields in the magnetosphere that sweep out these energetic electrons. But once you get into this descending phase of the cycle, we're going to get a lot of recurrent storms due to high-speed solar wind streams that for a period of time can be building up these energetic populations from electrons to relatively high levels where arcing becomes a problem. And so the basic physics problem here really is just one of charge accumulation in a dielectric. This diagram over here on the right is kind of a simple 1D model of internal charging. So if you have an electron beam, penetrating a dielectric, you're building up charge, as a function of distance in this dielectric, and that ultimately builds up a charge density, which has electric fields and potentials associated with it, and that's really what the equations say over here. And there's some control over this on you'll lose some of this charge through conduction currents, out to the edge of the dielectric, and you can dissipate that to a ground plane if you can ground it. There's also a phenomenon called radiation-induced conductivity, that the higher radiation flux into the material will actually increase the conductivity, and so you can actually short out some of the charge accumulation if you have high RIC components to the charge density. And you can see that, when you're looking at examples of charging in simulations here. I'll show you some examples here in a second on that. But again, this is just the basic one-dimensional version. There are some nice three-dimensional codes now available. In fact, the Charge Plus model that ANSYS distributes has a three-dimensional internal charging code included with it, and is much more sophisticated than some of the examples I'll show you here. But there's kind of two separate sets of models that are often used for, equation sets that are used for modeling of internal charging. One set of them is called the generation recombination model, and this is actually a pretty sophisticated set of equations. It has a whole bunch of parameters that has to do with drift carriers, loss through recombination, charge carrier pairs, a lot of parameters, kind of the detailed solid state physics of the materials and the charges, within those materials. We tend not to use that very often for engineering applications, and for the simple reason being that getting measurements of all those parameters are just tough. And you'll tend to see that maybe in science applications where somebody's studying some physical process, and they'll carefully go through and measure all those parameters. But it's tough to get some of the basic parameters for engineering, much less all these detailed sets of parameters. So we tend to use this other one called the radiation-induced conductivity model, and that's one where basically the conductivity is the dark conductivity, or just the intrinsic conductivity of the material, plus this empirical RIC component to a conductivity, and it's a much simpler equation set and a lot less parameters in it, and that's pretty widely used in a lot of the engineering tools for internal charging. One code that a lot of people use, and you can get access to this real easily through the SPENVIS website, is the European diktat code. It's a 1D model, and it allows a person to go do a really quick assessment on internal charging. I just got a couple of examples here. This is their input page in SPENVIS, where you're putting parameters in and run it. And when you run it, you'll get this information back out that'll tell you, for a given resistivity or a dielectric and the exposure to some radiation environment. In this case, I used what's the ESA flumic. It's a worst case geo charging environment. And it would tell you that if you had, for this particular material, it was 1 millimeter of mylar, if the resistivity was 10 to the 14 ohm meters, that after 48 hours, there'd be some charging current, there'd be a maximum electric field on the order of 10 to the 5 volts per meter, with the voltages, and just to note that this is probably not liable to breakdown, since the maximum electric field is lower than the breakdown field of 10 to the 7 volts per meter. And you can see if I go and I start increasing that resistivity, by the time I get 10 to the 16, then I'm getting electric fields on the order of 10 to 7 volts per meter, and now it is liable to break down. And if I go to 10 to the 18, I get even higher electric fields. And the nice thing about this code is they actually have, I think, some things in here that not only does it tell you that it's liable to break down, it may have some suggestions on what you can do to reduce those electric fields. But we use this a lot just for kind of quick studies, if you want to do some quick analyses, kind of first order charging evaluations along trajectory. So this is some examples of going through the Earth's radiation belt. This top example up here, what I've taken is a 10 centimeter chunk of plexiglass with a conductivity of 10 to the minus 15 Siemens per meter. And I've looked at 3 different cases of shielding. If I had aluminum shielding thickness of 0 centimeters or no shielding, or 1/10 of a centimeter or 2/10 of a centimeter of aluminum over it, I'm just looking at the electric field as a function of time. And all 3 of them come to an equilibrium after about almost 50 hours. And and of course, if there's no shielding, you get a much larger electric field, and this is all above 10 to the 7. There's a chance here that you get breakdown. But for these 2 values, they're much smaller electric fields at equilibrium because your shielding is reducing the electron flux to the dielectric on that. So you can do those kind of studies, really quickly. The bottom case down here is an example using the AE8 solar maximum electron flux, and this is for transit through the Earth's radiation belt. So this is outbound through the inner belt and the outer belt, out beyond the outer belt and back through the belt here. And again, you can kind of see this is a trade study on 3 different materials with 3 different conductivities, just seeing what the electric fields would be. And each one of these is a 1/10 of a centimeter thick. And so, Teflon is the worst for charging. In this particular case, borosilicate glass has the least charging on it. And so, again, it's a pretty simple tool, and it's pretty helpful to go through a lot of these things. The issue I have with this a lot is there's limits on how long it'll run. You can't do this for, this particular case here. I couldn't have done 20 orbits. It won't give me that much CPU time. It limits the amount of time you can run on that. And so typically, we can do these simple trades, but if you want to do something more sophisticated, then we'll go back to codes that we have source code for, and we can set them up and run them with our own parameters. But this is just a couple more examples with the dictat. In this particular case, looking at plexiglass, 10 centimeters, no shielding. Well, I think I've got an error here in my chart. I think one of these should have been one material and one of them should have been another material. I think I copied and pasted the wrong label over here. So, John, I'll fix that and send you an update to these charts here that has it corrected on that.
No problem.
Yeah. As I said, if we really want to do something for longer times or more detailed, we tend to use this NUMIT 1D code. NUMIT stands for numerical iteration. This was developed by Art Fredrickson over a number of years. Originally he was at AFRL and then later worked for JPL, and he developed these codes. And he used what's called the Tabata algorithm, which fits to a Monte Carlo electron transport code to get the radiation dose and the charge deposition. And that's nice because it runs really fast because it's an analytical code. It's not as sophisticated as a Monte Carlo code, so you can't do as much with the the geometry, but it's fast, and which is nice. And I've run 30 years of data from satellites using these codes, and you get results back in less than a few minutes on that. If you're doing Monte Carlo codes, it would take much longer. And you can do trades on material conductivities, dielectric constants. You can play around with the electron spectrum. You can use spectrums, monoenergetic beams. You can fix the flux to be constant. You can do time series with arbitrary durations, anywhere from hours to years if you want to. And the typical output is electric fields, the charge density, the currents, and the radiation dose rates as a function of depth of the material. And so the graphics down here on the left, this is just an example of one of the spectrum that we used as input. I think these are from Los Alamos satellites in GEO. The center panel figure here, the multiple panels, that's the electric field magnitude is color-coded on the top. The electric field is both positive and negative in the dielectric, and so I typically just take to color-code it, I just take the absolute value. And so there's a different sign depending on which, where this peak here is, or this black line right through here is the centroid where the potential is the greatest, and the gradient, the potential 0. So that's and where you get zero electric field because you don't have any gradient. And then the gradients on either side are where you have the really strong fields. You get charge densities. This particular case, I have some examples in here from a couple of the lines from the electron flux. And then on the bottom down here, it's just showing numerically the peak electric field, in the results for each one. The top right up here is just some examples of electric fields as a function of spatial distance through a material. So this particular sample is 100 millimeters deep, and I have different materials in here with different parameters, and I don't know what I was probably playing with here. It could be dielectric constants, it could be densities, probably densities as much as it's varying on that, and then that I can get dose down here as well on that, so I can get a bunch of different parameters out of that. And we use this a lot to just do, again, screening on materials over a function of time. But you got to keep in mind it's a simple one-dimensional model. But in this particular case, I've taken the case of 3 MeV electrons on that polymethyl acrylate material, or that acrylic block, and I'll show you why I did that one in particular. So this particular thing is about a 10 centimeters thick, and so I've done 3 MeV electrons, and I've used a beam current of 0.01 nanometers per square centimeters on that, and this is just the parameters I've used for the material on the acrylic. And so for the conductivity here is 10 to the minus 16 Siemens per meter. So it's not very conductive. So it's going to accumulate charge. And that's in fact what you see is the charge buildup, kind of near the front of the block. And the maximum electric field accumulates over time on that. And so again, just to emphasize, this is this PMMA block, that I was using for the examples here. And the electron penetration, it really only for these energetic electrons is only penetrating maybe a centimeter or two into the block on there. And again, that's kind of typically what you see here is this the charge damage, is this arc through the material. I think that this is where the charge was accumulating on the outside of the block, and then when it arcs to through to this ground point in here. And then we can do other trades on this, and I know I'm almost done here, but some other trades here. So this is a case where I've taken this 3 MeV electrons on PMMA, and I've used a conductivity now of 10 to the minus 14 Siemens per meter. So I've made it a little less conductive, and I'm going to turn the beam off at 1 hour. But because the conductivity here, there's really very little effect on the electric field over time. So this is the time period that the beam is on, and it comes to some equilibrium. And then once you turn the beam off, it basically stays the same electric field. And that's because the time constant for discharge of that charge density out of the material is on the order of, I think it should be 0.9 hours. I'll fix that one as well on that. If I change the conductivity, and this is not right here either. I'll have to fix that for you. I got a bunch of things to be fixed here. So this should be a much higher conductivity, and so it's more conductive. And when I turn it off, the charge density then decays. No, I guess that is right. That is right. Sorry. I think this numerical values are not right. I need to fix that. But the charge density here, the time constant decay is 91 hours, and we're not even close to that. So we maintain the electric field during this time period. At the higher conductivity, when I turn it off after an hour, then I see the dissipation of both the charge density and the electric field because the charge is conducting out of the block. And the error here is this numerical value here for the conductivity should be larger, not the same. And again, I'll fix that and get those charged to John. And I think finally, this is maybe one of the last ones here. is a case here where this is just charging in geo using this methacrylate block, and this is over 5,000 hours. And I'm using data here from the Los Alamos satellite, so you can see a series of geomagnetic storms as the plasma heats up and then decreases. You get a high flux and low flux and high flux. And what's interesting here is over time, this charge density will gradually build up over time, and particularly deep in the block where you're getting energetic electrons penetrating deep, it continues to accumulate more and more and more over time, and that's because at these low conductivities, you're just accumulating charge, over some period of time. And if you don't give enough time, from one event to the next, it'll continue to accumulate charge, and it may not come into equilibrium, for thousands of hours, which ultimately, could be days to weeks to months, depending on the conductivity of the material. And I think that's the last one here. So I'll go ahead and open it up for questions.
Well, thank you, Joe, for a very comprehensive presentation. We do have a few questions, so I don't know if you can see them, or I can certainly read them to you. If you click on the Q&A button, you will see 2 questions have come in. The first question is this: do you find different failure anomalies mechanisms to be dominant in LEO versus GEO? My recollection is that the LEO charging handbook largely focuses on issues with solar cells, whereas the GEO handbook does not.
Yeah, in fact, NASA's that LEO charging handbook of NASA, really, it's an unfortunate topic. I mean, an unfortunate title. It shouldn't be called the LEO charging handbook or standard. It should be called the solar cell charging, high voltage solar cell charging handbook. It really is talking more about high voltage solar array systems. And really the fundamental physics of charging, you accumulate electrons, and your spacecraft becomes more negative until you reach an electric field value that there aren't any more electrons in the environment that can approach the spacecraft, and then it comes to equilibrium. And if your plasma is not very energetic, that equilibrium field is low, and if your plasma is really energetic, that equilibrium field is very high, and it may approach the breakdown strength. And that's true whether you're in GEO or LEO. And I think really the big difference is that you can be in strong charging environments for many hours in GEO, whereas in the LEO environments, typically your auroral arc encounters are minutes or less.
Okay, a second question: can MMOD or MMOD impacts trigger discharges in charged dielectrics when the dielectrics are charged to sub-breakdown threshold?
Yeah, so there's been a lot of work on that over the years, and there's been some debates about that. There are some people in the community who argue that impacts drive the arcing rates, and then there are other people that say, oh, that doesn't make any sense. If that was the case, spacecraft would never survive, that we see arcing much more than we see impacts on it. But I think in reality, probably there's a little both is true. Certainly, if you have something like a solar cell or some dielectric exposed to the space environment, you're accumulating charge, and it's has an electric field that is is pretty close to breakdown, but isn't quite there. It may be just fine, but you can imagine if you get penetration by an impact event and it's producing localized plasma, and that shock event to it, it's probably going to be too much, and it's probably is going to arc. And so I certainly think that can occur.
And then I have one question as well, Joe. Looking forward, what do you think the biggest breakthrough or disruption will be in this field over the next 5 years?
Well, it's interesting. So, talking to particularly some of the people that have been around since the 1970s and the 80s, when charging first was observed, and there was a lot of work done to try to understand charging because the Air Force was launching satellites to GEO and losing them within a week. And apparently they got a directive from their senior management to figure out what was happening and fix it. And I think over the years, people have gone a long ways towards really understanding it. And, I've been told by, again, some of the senior, people that they think that both surface and internal charging is well understood. And there really is no reason to be seeing failures from that anymore. And if we do, it's because people aren't paying attention. But I think what we are going to see is these high voltage systems, and particularly high voltage solar arrays, because power needs are going to be going up, and in their photovoltaic systems are much more efficient at higher voltages because you don't need as much mass of wiring, to deliver your power, through a large vehicle if you run a high voltage system rather than a low voltage system. And so probably high voltage power systems are going to really be driving a lot of issues with charging, because when you get the string voltages up around 200 and 300 volts, you're up in the realm where arcing becomes a problem. And there's going to have to be a lot of attention to good design of the solar arrays to assure that they don't arc on that. And I think that's something we're going to have to confront here probably in the coming years.
That makes sense based on some of the things we're seeing. Well, if we don't have any more questions, thank you again for a very comprehensive presentation. To the attendees, just a reminder, we will be sending you a link soon to a recording of the presentation, so watch for that with your emails. Looking forward, we have another keynote coming, which will be held on Tuesday, July 1st at 11 a.m. And if you have any interest at all in electrostatic discharge, this is probably the presentation you don't want to miss. It is Dr. David Pomeranke, who's recognized as a world-class expert in that field, and he'll be addressing electrostatic discharge and how it is simulated. So I look forward to seeing many of you there as well. Again, thank you for your attendance. Joe, thank you again for your time on this. It's been wonderful. And I'll bid you all goodbye.